Hi students, today we are going to see the computation of fast Fourier transform algorithm. Fast Fourier transform is nothing but an algorithm used to compute DFT with reduced number of computation, which naturally gives the DFT in a fast manner. So this computational efficiency is achieved by decomposing an endpoint DFT into successively smaller DFT, which follows the divide and conquer approach here. So in direct computation of endpoint DFT, the number of complex additions is given by n into n minus 1, and complex multiplication is given by n square. So here in this direct computation, it clearly shows that the number of complex multiplication is more than that of the complex addition. So the time taken to compute this complex multiplication will be more than that of the complex addition. So in radix 2 FFT algorithm, the complex addition number of complex addition performed is given by n into log base 2 of n, and number of complex multiplication is given by n by 2 into log base 2 of n, so which clearly shows that the complex multiplication is half of the complex addition. So since the complex multiplication has been reduced, automatically the time consuming will also get reduced here. So for example, to compute your 1024 point DFT in direct computation method, the complex additions performed is n into n minus 1, where it is 1024 into 1023. So it is 10,47,552. But in complex multiplication, it's n square. So it's going to be 10,48,576. But in radix 2 FFT, the complex addition is given by n into log base 2 of n. So 1024 into log base 2 of 1024 is given by 10,240. So this log base 2 of 1024 can be calculated in calculator as log. In our calculator, it is log base 10. So to get it, log 1024 divided by log base 2 will give you the answer. A number of complex multiplication is n by 2 log base 2 of n. So this is going to be half of your addition here. So 5,120. So here we just see the difference here. So time taken to compute your 10,47,550. So, but here the time taken will be very, very less here. And similarly, you just see that too in this multiplication, there is a huge difference. So what happens? You are able to obtain the DFT results in a very fast manner using this radix to FFT algorithm. So the percentage of savings can be obtained by DFT computation minus your FFT computation divided by DFT into your 100. So here this is for complex addition. So 10,47,552 minus 10,240 divided by 10,47,552 into 100. So 99.02. And similarly for complex multiplication, it is 99.51 percentage. Now we'll see this algorithm here. By definition, the endpoint DFT is given as some x of k equal to summation n equal to 0 to n minus 1, x of n e power minus j2 by kn divided by n. So in this one, how this computational efficiency is obtained is, so we are going to capture the commonly used terminology. So where in all the multiplications, commonly a term can be identified. So here what happens, this k and n is going to get varied. So n by this summation and k is by this value here. But here this e power minus j2 pi and then this n point never going to be changed here. So I'll be taking that as a uh, one, that is your, to simplify this notation, I'll be taking this complex function as w suffix n, which is equal to e power minus j2 by n. So now this may be 2. I'll be substituting this w suffix n in this equation 1. So here this complex function w suffix n is called as a twiddle factor here. Right? So substitute 2 in 1. So summation k x of k equal to summation n equal to 0 to n minus 1 x of n w suffix n. So this entire term is replaced by w suffix n into kn. So for k is equal to 0, 1, 2, 3 up to n minus 1. So with the base of this equation, we are going to solve this one. So here the main thing is nothing but So repeatedly used function is can be made it as a the complex function is made into a twiddle factor so that will be able to compute it very fastly. So here, based upon the decimation algorithm, how we are going to decimate, the FFT can be classified into two types. One is decimation in time FFT algorithm, and the other one is decimation in frequency FFT algorithm. In decimation in time algorithm, the time domain of the signal will be decimated. Here in decimation in frequency, frequency domain of the signal will be decimated. So now we'll see the decimation in time fast Fourier transformation algorithm. So in decimation in time, as I said earlier, the time domain of the sequence x of n is decimated and the smaller point DFTs are performed. So the resultant smaller point DFTs are combined together to get the results of n point DFT. So this is a basic how we are going to proceed. So in radix 2 FFT, the time domain sequences is decimated until it is going to get a 2-point sequence here. So in radix 2 FFT algorithm, the value of n point can be obtained in how many stages? So is given by n equal to 2 power m. So since you're going to have it as 2 power m, so you're getting it as a radix. 2 is nothing but a radix and m is nothing but number of stages here. Suppose for example 8-point DFT. Now I can write this 8 into 2 power 3. So your 2 is nothing but radix. So till the 2-point sequences I'll be reducing, and 3 is nothing but the number of stages. So in 3 stages I'll be able to obtain my result here. So here, how I'm going to decimate now? This 8-point sequence will be decimated into 2 as even and odd. So 0 to 7 even, all your even 0 to 4, 6 will be one side, and then 1, 3, 5, 7 will be another side. So this n point is decimated into n by 2 point. Again, this n by 2 point will be decimated as even and odd. So 0, 2, 4, 6 becomes 0, 4 as even and 2, 6 as odd. Again, this 1, 3, 5, 7 will be decimated into 2 as even and odd. 1, 5, and 3, 7. So now this n by 2 is decimated into n by 4. So this decimation process will proceed until my last sequence is going to have only this 2-point sequences here. So this one, the decimation, your decimation is performed in a time domain. So we are saying this algorithm as a decimation in algorithm. So this is the basics we are going to follow in the Ducos algorithm. So now we derived, we have your x of n samples here. So this is an n sample. So we are decimating your x of n into two sequences of n by 2 samples. That is f1 of n and f2 of n. So f1 of n be your even samples x of 2n. So what happens? This n point becomes n by 2 point. Again, your f2 of n will be your odd sequence. So x of 2n plus 1 here. Right? So this may be your equation 5. Now you know that x of k will be n point DFT of x of n. F1 of k nothing but n by 2 point DFT of f1 of n, and f2 of k is n by 2 point DFT of f2 of n. Now, this equation 3, which we saw in the previous slide, is nothing but x of k equal to summation n equal to 0 to n minus 1, x of n, w suffix n power kn. Now, I'm going to substitute this fourth equation in this one, right? So, here, what happens, I'm going to split this x of n into x of 2n and x of 2n plus 1. So, and x of n is splitted as x of 2n and x of 2n plus 1. So automatically this n point becomes n by 2 point. And here I replace my n as 2n. So where and all I have n, I replace it by 2n. Similarly, here this x of n is replaced by 2n plus 1. So this n is replaced by 2n plus 1. Now, this may be your fifth equation. You know it very well. W suffix n, twiddle factor is nothing but e power minus j 2 pi by n. So this W suffix n, 2nk can be written as this W suffix n is nothing but e power minus j 2 pi n, and this 2nk can be written as such. So now you know the rule. Numerator can be written as denominator. So this 2 can be written as denominator is n by 2. So it's if your denominator is n, I can write it as w suffix n. Say here the denominator is n by 2, so I can write it as w suffix n by 2 power nk, because I'm just converting my n point as n by 2 point. So all should be in terms of n by 2. So let it be 6. Now I'll be substituting the sixth equation in the fifth one. So what happens here? So W suffix n by 2 into n. Okay. There it is 2n plus 1. I have written a plus b. E power a plus b can be written as e power a into e power b. So I wrote this one, and you know this value of W suffix 2 power nk can be written as W suffix nk. So this is nothing but a constant value according to this summation. So I took it out. So now you know that one. So this can be written as f1 of x plus W suffix k n power k into f2 of x. So this n point DFT is split into 2 n by 2 point DFT according to your even and odd here. So this is going to be the first stage of computation. Again, what happens? This n by 2, this n by 2, f1 of k and f2 of k will be splitted. It is even and odd. And before that, you have a phase factor with a periodicity of n by 2. So for this periodicity, I can write it out as W suffix minus W suffix n power k. Right, so decimate this f1 of n as even and odd as v11 of n and v12 of n. So, but so the sequence becomes n by 4 point, right? So this f1 of k can be written as summation n equal to 0 to, so this one. So this f1 will be split into f1 2n and f2 of 2n plus f1 of 2n plus 1. Same thing as the previous part. Again, this n by 2 12 factor should be converted into n by 4. So this n by w suffix n by 2 is nothing but e power minus j2 by into divided by e power minus j2 by divided by n by 2. So here this 2n numerator is nothing but denominator is denominator. So I can write it as n by 4. So it's nothing but w suffix n by 4 power nk. Right, so I replace this one. F1 of 2n is nothing but v11 of n, and this middle factor will also get changed. This is v12 of n. So now this 2n plus 1 into k can be splitted, and then you can write it out. Now what happens? I can write your f1 of k is nothing but v11 of k plus w suffix n power k into v12 of k. So here this f1 of n is going to be n by 2 point sequence, but this v11 of k and v12 of k is going to be n by 4. So this gives you 10th equation. So similarly, I can write decimate your f2 of n as even and odd, which is nothing but v21 of n, v22 of n. So what happens? I can write this f2 of k is v21 of k plus w suffix n by 2 power k into v22 of k. So here this f2 of k is your n by 2 sequence, n by 2 point sequence, but your v21 of k and v22 of k is going to be your n by 4 point sequence here. Right, so I can write your v11 of k, v12 of k, v21 of k and v22 of k as this way. Right, so this all the sequence is going to be of n by 4 point sequence here. So now I can perform again still like v11 of n, v11 of 2, so v11 of n, v12 of n, v21 of n, v22 of n is can be splitted again as even and odd, and it goes on. So this decimation of data sequence can be repeated again and again until the resulting sequence are reduced to 2 point sequence, because this is your radix 2 DIT FFT algorithm. For further clarifications, you can contact me at bangalore.blogspot.com. So we can see in the next presentation. Thank you, students.